of the heuristic pursuits. I mean, the claim of modern physics is that we understand, certainly in broad sweep and in some quite remarkable intricate detail, the history of the universe in the sense of its evolution from the first fractions of a second after the Big Bang, billions and billions of a second after the Big Bang, all the way through to the formation of structure in the universe today, in the vast observable universe, but in a possibly infinite universe beyond. I should say, I must say, right at the start of this tonight, there's a drinking game, which is, it's very famous in the UK. When Wonders of the Solar System, or whatever it is on, then on the web there's a whole page, and it says, if I say millions, you have a drink. If I say billions, you have another drink. If I stand on the top of a mountain aimlessly gazing at the sky, drink. And it's very popular, and there have been no casualty admissions so far. But already I've said millions and millions, so that means at the interval, you go to the bar, get 2 drinks. The best way I have, I think, of introducing this, as I said, a hubristic pursuit almost, is to show one of the most iconic pictures in the history of astronomy. Pictures taken by the Hubble Space Telescope called the Extreme Deep Field Image. And it's a picture of a piece of sky you would cover if you took let's say $1 coin and held it about 25 meters away. So you imagine the tiniest piece of sky that would cover. This is also a picture of it. That little diamond there that says XDF is the size of that piece of sky relative to a full moon. So the tiniest piece of sky. And what the Hubble Space Telescope did was, over thousands and thousands of seconds, it opened its camera and took a very, very long exposure picture of that tiny piece of sky. Now, that piece of sky was chosen deliberately because it was not particularly interesting from the surface of the Earth. So there are no beautiful galaxies visible in that patch of sky, no nebula, nothing of interest at all, really. But this is the photograph that Hubble revealed when it took a long, long exposure, the extreme deep field image. And you see that it's anything but empty. It's full of structure, full of points of light. And you see that it's also full of shapes. They're all galaxies. There are over 10,000 galaxies in this image. Remember, again, it's that tiniest piece of sky. The most distant galaxies in this image, which are some of the most distant structures known in the universe, are over 13 billion light years away. That means light travelling at 186,000 miles a second took 13 billion years to journey from those galaxies to us. Most of that journey took place before the solar system was formed. So it's an immensely, I think, awe-inspiring image. You imagine extending that over the entire sky, so 10,000 galaxies in that tiny piece of sky, you get images like this. This is a galaxy map of the observable universe, so a sphere surrounding the Earth with all the galaxies we know of as points on the map. And just to set the scale, that's the 1 billion light year ruler there. So it takes like 1 billion years to get across that piece of the map. There are something like 350 billion large galaxies in the observable universe, each with on average, between 100 billion and perhaps 1 trillion stars like our sun. We've discovered, by the way, in the last few years, that many of those have solar systems around them. Virtually everywhere we look in the night sky now, we see stars with solar systems, with planets. 350 billion large galaxies, more than double that number of smaller dwarf galaxies. So I suppose what I'm trying to say is the universe is a big place. In fact, it may well be infinite beyond that boundary. We have evidence certainly that it stretches beyond that. So the idea that we can even claim, or begin to claim, or even aspire to understand where that came from, how those structures formed, what are the laws of physics that underlie that structure formation, is remarkable. And it really is a 20th century and 21st century pursuit. What helps us is a simple fact, which is difficult to understand and explain. I think it's fair to say there is no real explanation for this. But what we find is, if we imagine rolling the universe back, so the universe began at the Big Bang, then expanded and cooled. It's been expanding, by the way, 13.798 plus or minus 0.035 billion years, which is one of the most remarkable measurements in itself, the age of the universe, now pinned down with such precision. But if you imagine winding it back, today it's an old and cold universe full of structure. But as you go back, the universe heats up because it contracts, those structures melt away. And what we found is that you go back in time further enough, so you go back to the first instance after the Big Bang, then the laws of physics are simple. The universe is simple. It's intelligible. There are a very small set of simple laws and simple building blocks of nature that reveal themselves at those very high temperatures. And in a sense, the history of the universe has been a history of complexity crystallizing out and obscuring the underlying simplicity. I think a beautiful image to have in your mind is of a snowflake in the palm of your hand, which is a tremendously complex and beautiful structure. Each one of them is different, intricate in many ways. But as your hand heats the snowflake up, it will melt into a pool of water, and you'll see that it's nothing more complicated at the basic level than hydrogen and oxygen, molecules of H2O. The complexity emerges when you cool it down. In a very similar way, we see that our picture of the universe is that it expands and cools, complexity crystallizes out. And what I'm going to talk about quite a lot tonight is how we understood that, how we did experiments, what data we were able to see, what pictures of the universe helped us in developing that story. So we have this sweeping idea of a hot universe, expanding, cooling, complexity appearing. Data, how do we know that? Well, I think this is one of the most beautiful images. I showed the Hubble deep field, so I just swallowed a cracker or something. I was eating those cream crackers earlier. It's not wine yet. There we are, that's better. So I showed the Hubble deep field image, one of the most spectacular images in the history of astronomy. This is one of the most recent images. It's an image that was released, or data that was released this year. It's from a satellite called the Planck satellite, and it's an image of what's known as the cosmic microwave background radiation, which is essentially the oldest light in the universe. So the picture is that as the universe expanded and cooled, at a very precise moment, around 380,000 years after the Big Bang, the universe was cold enough for atoms to form. So before that, the universe was in a state known as a plasma. It was too hot for atoms to form, so you had electrons and photons and the basic atomic nuclei all densely packed together, far too dense for light to travel very far. So the universe was opaque. So you can't see back beyond that point. But at that point, 380,000 years after the Big Bang, it cools down, atoms form, the universe becomes transparent. Light is released from that time, and it's been travelling across the universe ever since. And what we've been able to do is take a photograph of that light. Now, it began life as light, as visible light. The universe was extremely hot at that time, but the expansion of the universe has stretched that light, stretched the wavelength, and so the light is now in the microwave and radio parts of the spectrum. And this is an image of it. The different colours represent essentially different temperatures in different parts of the sky. The reason it's that shape, by the way, is you're imagining a whole spherical map of the skies folded out, flat, like a map of the Earth. The different colours represent very slightly different temperatures in the sky. And by very slightly, it's the tiny variations. The whole sky glows very precisely the temperature of around 2.7 degrees above absolute zero. 2.7 degrees of absolute zero. That's the echo of the Big Bang. That's the remains of the heat of the initial fury, the origin of the universe. And the variations in temperature are 1 part in 100,000. So tiny, tiny, tiny variations. They're represented by the different colours on this map. But they are vitally important. See, these colours, these different temperatures, represent different, very slightly different densities in the early universe. And those are the points around which the galaxies began to form and the clusters of galaxies formed. So, first of all, if this photograph was completely uniform, if the temperature were exactly the same, then galaxies wouldn't have formed in the universe. So there would have been no one there to look at it. There would have been no complex structures in the universe. In fact, George Smoot, who was involved in the first detailed measurement of the cosmic microwave background, said that an earlier version of this picture was like gazing at the face of God, because what you're doing is looking at the seeds, the origins of us, the origins of the galaxies. But there's more than that to this picture. It's remarkable in itself that we're able to see and measure those seeds. But you can ask yourself, well, what's the origin of those fluctuations? And for that, we use theoretical physics, but we have a reasonably, if not widely or completely accepted idea, a very plausible theory of where they came from. And it is remarkable. The idea is this: way back, so we carry on back from 380,000 years after the Big Bang when this light was released. Carry on back, go all the way back to when the entire observable universe was less than the size of a single subatomic particle. So way less than the size of an atom. Something the size of an electron, which we can't actually measure. It's point-like as far as our best particle accelerators, the biggest microscopes we have, can tell us. So you imagine all the 350 billion large galaxies compressed into something the size of a single subatomic particle. At that time, which, by the way, for the drinking game, is a millionths of a second after the Big Bang. In more scientific language, 10 to the minus 36 seconds after the Big Bang or so. The universe would have been described by quantum theory. The quantum fluctuations would have ruled the universe. Now, what they are, our picture of the subatomic world is that things are always fizzing into and out of existence all the time. So particles and antimatter particles fizz into existence and pop back in and into existence back in. So the universe at subatomic scales is kind of a fizzing mess of little fluctuations as dictated or governed by the rules of quantum theory. So the universe is fizzing away, and then we think that something happened to cause the universe to expand extremely rapidly, exponentially fast. Space and time was stretched much faster than the speed of light, and the universe grew in the tiniest fraction of a second to something about the size of a melon, which is big on these scales. A huge exponential expansion. It's called the inflationary expansion. And in that expansion, the quantum fluctuations were captured, so mid-fluctuation, frozen and expanded to large distances, millimetre and centimetre scale differences. So they're frozen into the universe. Then, 10 to the minus 32 seconds after the Big Bang, that inflationary expansion stopped, and the universe carried on its more sedate expansion to what we see today. And when you do the calculations, so you use the quantum theory that we know of, you put that inflationary idea in, you do the mathematics, you see that those fluctuations should be magnified to precisely the distribution that we see in the cosmic microwave background. So it's a remarkable piece of physics that story has verification. And remember, I'm talking about things that happened when the 350 billion galaxies, or the stuff to make them, was compressed into something way less than the size of a single atom. And we have, if not a complete understanding, certainly a reasonable understanding of how physics at those scales may have translated into the structures that we see today. And when I say reasonable understanding, I want to show you one graph tonight, so I'm not going to scare you anymore. Get it over with early. But this is the graph I want to show you. What it is, it's a representation of that photograph. So essentially, that photograph was showing, if you remember, temperature differences across the sky, very slight temperature differences in this ancient light. You can sort of plot that. Over here, that says 0.1 degrees. So that's telling you something about the correlations, the similarities and differences between temperatures on scales of about 0.1 degree on the sky, so very close together. Then at this end of the graph, you've got 90 degrees, so that would be looking at correlations from the sky there to the sky all the way over there. The red points, and this is the key point, the red points on that graph are the data points extracted from that image, from the measurements of the cosmic microwave background radiation. And the green line is the theoretical prediction containing everything that I just spoke about, so the standard cosmological model, if you like, including that inflationary period, all that strange physics I talked about. The remarkable thing, the red dots, by the way, for the more scientific amongst you, have error bars on them, so they show you the uncertainty in the measurement itself. You see that green line goes straight through. It's absolutely remarkable. So it's confirmation that our story of the origin of the universe, our picture of its expansion, is broadly correct, except, and this is the level of precision we're acting with that word, people worry about that point. Look at that. There's one little blob there One little data point which sits well outside the theoretical uncertainty. It sits there, it doesn't fit with the model, and people are worried about that now, that point. It's a representation of some problems. Actually, there's for example, there's a cold spot which is slightly colder than the rest in the southern part of the sky. So actually the sky in Australia, there's a piece of cosmic microwave background that's a bit colder than it should be, statistically. And people are even beginning to suggest now that that's perhaps the imprint of another universe or something, some other piece of the universe, perhaps in another dimension, that's either touched our universe or was close to it in the past and changed the expansion rate a little bit. People are talking about cosmic voids, where for some reason there's less structure, which means the universe isn't the same everywhere, which would be a tremendous shock. But the reason I said it's all speculative stuff, but I think the message I wanted to get across is that cosmology, the observation and understanding of the evolution of the universe, is now a precision science, a high precision science, and it hadn't been that before in the 20th century. It's only in the last 10, 15 years that it's become a really high precision science. And just to end this part, I wanted to leave you with what we're going to do next, because these theories now need testing. You know, is it true? Are we really on some kind of sheet, some four-dimensional sheet in a high-dimensional universe? What did happen at the Big Bang? We don't know. Why did the universe begin in a highly ordered state that's been getting more and more disordered since? Even though my song, Things Are Gonna Get Better, ran counter to that simple law of physics called the second law of thermodynamics. If I'd have known what I know now, I would not have allowed that song to be written for that reason. It's one of the big mysteries. Well, let me just leave you in this part with this photograph. Well, it's not a photograph, it's an artist's impression of a new instrument, a new astronomical instrument called a Square Kilometre Array, which is being built partly in Western Australia. So it's a Southern Hemisphere based project, but a global project. It's the world's largest radio telescope. It's many, many small radio telescopes working together. It will function as a radio telescope with an area of a square kilometre, hence the name. And it will be incredibly sensitive. It'll be able to probe the universe in unparalleled detail. And there's just one PR number that I like, which no one expects to be used, but it's kind of intriguing. It could detect an aircraft landing radar within 50 light years of the Earth. It's that sensitive. So really, if anyone's flying a plane around in our neighbourhood, we'll see it with this telescope. It'll probe the universe in unprecedented detail. So with that, that's just by way of introduction, of a little skim through the brief history of the origins of the universe. I've talked about the origin of structures, the strange intelligibility, if you like, of the laws of physics. I'd like to introduce a colleague on stage to help keep me on the straight and narrow a little bit. I think he's either the most intelligible or unintelligible structure in the universe. Ladies and gentlemen, it's Adam Spencer.
Sydney for an evening of science with Professor Brian Cox. Give him a round of applause. I'm saying you never need to apologise for a good graph. The mathematically minded like myself in the audience, graphs are basically pornography. Let's be honest. So
that's why I took two of them out. You stole them, didn't you? To his hotel room.
So big that we're here tonight in Sydney, which really is one of Australia's scientific powerhouses. We are literally just down the road from Australia's oldest university, the University of Sydney, with, get this, Brian, buildings dating back to the 1850s. It was at the University of Sydney that John O'Sullivan did his PhD. He wanted to work with the CSIRO, and while working up the mathematics of reading Hawking radiation from distant singularities, came up with the same Fourier transform mathematics that now powers Wi-Fi around the world, bringing in $200 million a year in royalties to Australia. And we have, of course, in Sydney Harbour recently showed to have more species of fish in it than all of Europe combined. So there you go, England. Sure, you've got the Ashes, but human diversity in your face.
Science, so is it counting fish? Just something that happens to be there. It's not down to you, is it, personally? Whereas the failure to bowl line and length.
We might move on from this one. This is going to be a great show, right? For many years now, this man's been asking the big questions and bringing the answers. But tonight he'll do more of the same, but with a bit of difference as well. We'll also get later in the show to ask some questions of Brian Cox. I'll be around in the audience, and right now I'm going to ask some questions of the Brian Cox that we saw before he came to television. Let's meet Brian. Give him a round of applause. Come to the seats, Brian. I did mention in the introductory video piece there, I called you an amateur electrician. You were quite geeky from a very young age, weren't you?
Yeah. It's true, though, that that's a badge of honour now, isn't it? It wasn't, was it? Now the geeks will inherit the earth. It is now. It is. We are. It's like predictions. Absolutely. But yes, I was. What I was interested in when I was little was primarily wiring up my granddad's shed. And I asked, when I was the age of 7, I think, I asked for a fuse box for my birthday. I remember it was a 4-way, it was a wireless consumer unit. It had, I think in Australia, it had white fuses in, which meant there were 5-amp fuses. I remember it really vividly. Blue was, I think, 50 and red was 30. Yeah, it was stuck in my head. So I was that geeky that that's what I wanted to do.
On the rare occasions that you got out of the shed and into the house, here's a walk down memory lane, please. Have a look at this photo. You were not a train spotter, a bus spotter. Yes.
Yeah. What I used to do, and the important bit, by the way, is my little laser, is this number here for a bus spotter. It's 81.
So I would have thought this was the 416 from old.
No, what matters is this, it's a chassis number. And then what I used to do, I had a book of these numbers, and I used to sit in my mum and dad's house, and when they went past the window, I used to tick them off. And so when I crossed them off, I had the small things. There's like this one here, you see, I would be interested in 2045 there. Class 51, this thing, by the way, we can't roll one body work. And I got that, the sad thing, this little boy really into buses, because I like big machinery, and I crossed them off. And I've still got the book, and I only got about 8 of them, because my mum and dad didn't live on a busy bus route. I was just sat there for hours, but
finally you broke out of that, your life changed a bit when you had to take your little sister to a concert.
Yeah, I was, who is a Duran Duran fan? Not many. Last night it was fun again.
They're more sort of Thursday thing, true.
Yeah. It was nice. I think it was 15 or so. My little sister was 13, and my mum and dad, she was really into Duran. I was in my shed, polishing my fuse box, metaphorically speaking. I had a couple of graphs. And they were knocking on the door. Put that graph down. Take your sister to the wiring diagrams away, and take your sister to the Duran Duran gig. And so I went to this Duran Duran concert, and it was just a revelation because it was just the reaction to this band. You know, it was just hundreds of thousands of teenage girls just screaming at this band, and I thought. That's what I would like to do. I won't have to polish my own fuse box anymore. Anyway, so I thought, I just wanted to be a pop star. So there was no artistic kind of idea. I taught myself how to play keyboards, so just with the specific intention of being like those guys, like Duran Duran on the stage. I really want to do it.
And you go to a band called Dare. We saw a bit of footage of them earlier.
Yeah.
Big hair.
Yeah.
Big hair.
And one of those pictures, actually, there was a very quick picture. It was my 21st birthday, and it was in Florence, in Italy, because we made an album. We supported Jimmy Page with their first professional gig. It was an incredible thing to do. And then we supported a band called Europe. And
the final countdown.
Yeah, we did loads of shows with him, and that was one of those little clips. Was at my 21st birthday in Florence with Joey Tempest. Do you remember it? Yeah. Singing "Happy Birthday" on an acoustic guitar. It was an absolutely bizarre experience. And I used to get my hair like that by spraying it with hairspray, and then get these things called crimpers, which are these hot sort of things, and just went. And made it just stand there. I've no idea why I did that. Even in the 80s, it was a ridiculous thing to do. So like the rock band, we made 2 albums, and remarkably lucky, we made one at Joni Mitchell's house in Los Angeles. It was an incredible time. But after about 4 years, we had a fight in a bar, literally.
As in a literal fist fight?
Yeah, just stopped. And I came back and applied to do physics at Manchester University the day after.
As a lot of people do when they drop out of rock bands.
They're in the band school, so. Yeah.
But then this is so how did you get into D-Re?
That was so. I applied to university. I think we split up at the wrong time in the educational year. It wasn't planned very well. I think it was October, and you can't go to university until September in Britain anyway. So I got a summer job, like being a sound engineer for another band, and that was D-Re. And I used to drive them up and down the motorway. And it was just Peter Cunner as the singer, and a bongo player called Wendon. And we used to drive up and down in my car. And then I remember one day, they didn't have any songs, but I do remember famous song, Things Are Gonna Get Better, being written on a sort of thing, a piece of paper that wrapped up a Cornish pasty that we bought from motorway services. And I remember this music going, and
let's have a look at it now. It is a song that changed.
It was originally hit in '93, and I think here as well. Yeah. And I didn't come here on the tour, actually, because after that time I was in the second year of university, and I was doing my degree and I was doing exams, and there was a choice. It was either come to Australia with D-Re or basically leave the band and stay at university. I stayed at university that time.
You did meet one of your idols on Top of the Pops.
Yeah, I remember, I don't usually get autographs, so I've never really been interested in it, but I was on Top of the Pops and the Bee Gees were on. And but I was also Take That were on, who D-Re supported actually. And I remember I sat there and I was revising, because I was sat there going, I'm doing a physics exam, and I had a syllabus, a quantum mechanics syllabus. And I was really, and Robbie Williams came in and said, I've got to get their autograph, I've got to get it, have you got any paper? And all I had was my quantum mechanics syllabus. So I ripped it in half, I gave half to him, and I had half to him. And we went in and went, Mr. Gibb, come here. So we got them. So my image is somewhere in Robbie Williams' palace that he has now. He's got this framed Manchester University quantum mechanics syllabus with the Bee Gees signature. I once had a ceremony where we reload flash of light.
You chose academia over the rockstar life, even though you only got a D in your final year high school mathematics.
Yeah, I mean, at the time, I could always do physics, but maths didn't come easy to me. And I've noticed, I know you did a PhD in maths, didn't you? But I've noticed that that's common to many scientists, and a lot of physicists actually. And it requires practice. And I learned later, I say this to schools when I go to schools all the time, don't worry about it if you just sit down and you can't do maths. Because it's like playing keyboard or learning how to play guitar. Most people have to practice, and most people can get good enough to be a professional scientist that way. And you have to do it because it's the language of nature. It's undoubtedly the language of physics. Why nature is written in that language can be seen as one of the great mysteries. There's a very famous essay by a physicist called Eugene Wigner called The Unreasonable Effectiveness of Mathematics in the Physical Sciences. And actually I'll talk later about the Higgs particle and the fact that mathematical prediction, which was based on an aesthetic sense about mathematics, turned out to be correct. Remarkable. So for some reason mathematics describes nature. I mean, it could be. It doesn't have to be a mystery. Some people suggest that it's because nature's regular, We don't know why it's regular, but it must be in order to have regular structures like us in it, as part of the universe. So therefore, you would expect some kind of mathematical language to be appropriate, because maths describes patterns, describes relationships between patterns. But then you can also take the view that it's better than that. There's something deeper than that, and there does seem to be.
So you start working at CERN on one of the large hadron projects, and we'll hear about that soon.
Only one.
But how did the
Do you know, by the way, that you type that into, a few years ago anyway, you typed into Microsoft Word and the spell checker, and you said Large Hadron Collider, and it always underlined Hadron and Collider in red. And so I thought, why doesn't it know this? It should be culturally significant. But you say, okay, well, change it to what you think. And it changed it to Large Hard-On Collider.
But where did the meaning come from? Where did the TV career?
A complete accident. I think, and it's happened to several academics actually in the UK. But what happened, I was at CERN, so I was doing a postdoc, probably about 2005, I think, or something like that, 2004. And they came and interviewed me about the LHC, which was being built at the time under construction. And they liked what I did. And then 2005 was Einstein years, the 100th anniversary of relativity and his contribution to quantum theory from the photoelectric effect, and the Brownian motion, which is often overlooked, which is Einstein's great, really the final confirmation that matter was made of atoms. It was a calculation of how you would see pollen grains move around in water, given that you assume that atoms are instant. And so that year they interviewed me again about Einstein, about relativity, and then again, and then I made a little program, and then eventually I made one for the solar system, which was the first big series that I made. But I think the BBC actually, to be commended for this, it's one of the things that public service broadcasters, the ABC as well, can do, is they can go and they can give academics time to learn. You've got to learn how to present television programs. Local people, it's not a natural thing. You learn how to do it. And so there's quite a few academics actually. There's Professor Ian Stewart, who I don't really get his program, how he made us, and Alice Roberts, who's an anthropologist. And so they gave a lot of us time, and that's how it happened.
But it's not just Wonders of the Solar System, it's not just a show, 6 million viewers at a time. First ever BBC factual program to go #1 on iTunes.
It's getting a bit specific, that, isn't it? So the first BBC factual program about the solar system, which begins with some music and has a bloke on a mountain, sold 80 copies a minute for 3 days.
There you go. How sudden and how big does the fame get?
It was very fast for me in Britain actually, because Wonders of the Solar System was almost an overnight success. And suddenly you get asked to go on chat shows and the Jonathan Ross show, a Graham Norton, and those things. And it makes it difficult. Some people often say to me, they say, you must earn a bit of money there. You can't do earn some money from all these things, but then you spend it all again getting taxes because you can't go shopping. Because when you go shopping, it's just that people ask you, with all the goodwill in the world, they tend to ask you very technical questions about things. When I'm just really groggy in the morning, I just want some milk and coffee.
That doesn't just happen in the United Kingdom.
No, it hasn't. It happened once. We were filming something, it was in Oklahoma. And so you don't really associate Oklahoma with intellectual disservice to the people of Oklahoma. Good music. Jackman famously. So I went into a petrol station, a gas station, to get some petrol for the car. And then I walked up to the counter with them to pay. And the guy stood there and he fixed me in the eye and he said, "String theory." The fact that it requires an 11-dimensional space could be a model, a mathematical model, showing some underlying structures. Or it could be real. There could be real dimensions, it's about extended dimensions. There could be these Calabi-Yau manifolds that are curled up in small shapes. Perhaps those have a relevance to the number of generations of matter in the universe. And I just thought, either he said that to everyone, or somehow he watched my show. To this day, I don't know.
So, this is your lucky day.
Yeah, he sat there, and unfortunately for him, So, as
much fun as it is standing on the mountains making the TV shows, doing this sort of stuff, do you miss the academia? Do you miss just sitting there poring over the data, hoping you might see something?
Yeah, a lot actually, and but it's common to all middle-aged academics, if there are any in the audience, or even older academics, will say that. What happens to you is that your golden years are when you're a postdoc, you do your PhD, you get your first jobs, and you can just spend all the time you want on data. And it is wonderful. I worked at an accelerator called DAISY in Hamburg, which was an accelerator that collided electrons with protons. And I was working at a really esoteric branch of physics called diffraction, where the sort of photons actually just glance off protons and they can be knocked into something else. It's kind of interesting but esoteric stuff. But what you know is, even though it's esoteric, you're the first person in the world to see that data. It's fresh data, and you analyse it for the first time, and you make discoveries. And no one knows about that. You generate new ideas and new knowledge and new physics. The tiny backwaters, almost certainly for everyone. Very occasionally someone makes a big discovery. But that doesn't take away from the excitement, because I think it's that idea that you're learning something new no one's known before about the universe, even in a small corner of knowledge.
So you're saying that even if you weren't in television now, at this stage of your academic career, you wouldn't be doing that sort of stuff?
Yeah, I'd be, you end up managing or filling in forms or running a department or something like that, and you do, so it gets taken away from you. So it would be wrong with me, sometimes I say, things like this, I'll say, well, it's just a shame, I would love to go back, and I still teach at the university for that reason, I enjoy it, but I'd love to really get some research done. And my friends will say, well, but you are sat on the stage in Sydney, this beautiful city, talking about yourself. So it's not that tragic, is it? I suppose it's not, no. My goodness, fallen off now, I've just put it there today.
Let me ask the other really big scientific question in the world of love. Doctor Who. The new Doctor. I have to ask, were you approached for the role? The most awesome Doctor.
Just had to stand there with this balsa wood cube and just say, we don't understand what this is. And then I said, and I look at the camera and I go, you'll have to ask a better man than me. And he looks at me. So, yeah.
What is
that's my acting, that's no one can ask me that.
Why is Doctor Who so successful?
I think at its best, it's good science fiction. And science fiction is, I think it's underrated as an art form, because what it can do is it can address massive questions, almost circumvent them a bit. So the one I remember that I love, I grew up with Star Trek, Star Wars. Star Trek, I remember a great episode where it was about, do you remember the one where these race of people had a black face and a white face, half black, half white, and they were having a war with each other. And it turned out that they're in a war because one had the right-hand side of their face was black and the other the left-hand side of their face was black. And in the 60s, to write a program just overtly about racism and the stupidity of racism, to do that, but through in this medium where you're in space and you've got William Shatner and things like that, kind of and I think that's at its best science fiction will do that, and Doctor Who at its best does that. I mean, it's also, there's a channel where they run around a lot with monsters and things, but at its best it addresses big questions.
But do you, Neil, still at your age now, knowing the things you know and having had the experiences you've had, do you still have those occasional moments of 13-year-old wonder?
Yeah, yes is the answer. And often it comes from the television, the idea that I get put in with Wonders of Life, for example. I had to learn about biology, which I thought was an art for many years. ceased in the 1980s at school. And then, so when the idea for Rules of Life came up, and the idea that you could do a physicist's view of biology, based on a book by Erwin Schrödinger, actually, called What's His Life. I got taught biology by one professor from UCL, one professor from Manchester. And the idea, what I knew about physics, the idea of going under the solar system actually, was we had this idea that we wanted to, what's your ambition for it? Our ambition was to teach people or cause people to look at the night sky in a different way. So just when you go out and you see a sky full of stars, very beautiful, particularly in Australia, you're looking towards the centre of the Milky Way, but see that differently. See it as not a sky full of lights, but a sky full of worlds. See those points of light as suns. Know that there are solar systems around those suns. You know that you can see there's a galaxy there, the Andromeda galaxy, you can see with the naked eye, billions of suns in the Andromeda galaxy. So once you know something more about the sky, you can transform it, and that's what this word wonder comes from. And I found that in biology. I knew I wanted to, but I'm not a biologist. But going through the series, filming the series, I learned more and more. I found that Darwin's theory of evolution by natural selection is tremendous in its precision. So it's not just a wishy-washy idea, it's nebulous, it's really as precise as Einstein's theories, I would say. But then I remember a wonderful moment that happened to me I wasn't expecting. Right at the end of filming, and we were filming in Madagascar,